Okay, so in this one we have a small wedge. I'm just going to draw the picture instead of reading the problem. So it's on a rod that is spinning, and then here's the wedge, here's theta, and the length is L. And then the car has, or the object on the top has a mass M. Let's clean that up. And let's see if there's any other information. Okay, and so when the object sits at rest, that the speed has to be whatever it is. Okay, so basically we want, if it's going to sit at rest, then it's only going to have centripetal acceleration, and it's not going to be, it's only going to have an acceleration this way. But okay, so anyway, that'll become more clear as I draw the free body diagram for it. So for the mass, we have the weight down, and we have a normal force up. And let's go ahead and actually draw this a bit more realistically. So it has some kind of normal force from the wedge, and we want it to stay not going up and down the wedge. So we basically want the acceleration in the vertical direction to be 0. And then it's okay if we have some acceleration in this direction, because that's going to give us, because it's moving in a circle, so we'd actually expect it to be having some centripetal acceleration to the left. So basically we want is this, so if this normal force points like this, and this is theta, yeah, let's find a formula for the vertical component of this normal force. So let's label everything. I've done this enough times to know that this is theta, and you can kind of draw out a bunch of triangles to sort of convince yourself. So this is theta, this is 90 degrees, and then this whole thing is 180 degrees. So 180 minus 90 minus theta. So this angle is going to be 90 minus theta. So this angle is also theta. Sorry, that's a theta. And then if this is the normal force, then the vertical component is normal times the cosine of theta. And we want that to equal the weight, which is just mg. So that makes sure that we're not moving up and down. And then to relate that to the speed, let's think about the centripetal acceleration. So we want the sum of the forces in the horizontal direction to equal, we know that that's going to equal some mv squared over r. And then the horizontal force is just going to be the normal times the sine of theta. And so now what we can do is we can sub in for this normal force here, because we don't know that. So we can sub in here. So from this, we know normal is mg over cosine theta. And so we get that mg times sine of theta over cosine theta is tan theta, equals mv squared over r. And so we get that, oh yeah, and then what is this r that I actually refer to? R is the distance between here and here. So we know this r is going to be equal to L cosine theta. So actually, I'm just going to leave this as sine theta over cosine theta. Because I anticipate cancellation. So I'm going to sub in r equals L cosine theta. And from this, we get that you can just cancel out the cosines, bring the L over. So you get, and you can also cancel the M's. So you get V is equal to LG times square root of LG times the sine of theta. And just to review this problem, we wanted the vertical forces to be equal to 0, so it didn't slide up and down. That was this equation. And then the centripetal, and then we had the equation for the centripetal force, which relates to velocity. So here's the sum of the forces in the horizontal direction, just the normal times the sine of this angle. And we can set that equal to the centripetal acceleration. And then the rest is algebra. And yeah, if you want to convince yourself of these angles, I mean, just draw out all the triangles, make a pretty drawing, use straight lines.